Okay. Hello, everybody. Today is June 27th, and this is another SIG scheduling meeting. Remember that this meeting is recorded, and it will be uploaded to YouTube. You should, if you participate, you should adhere to the CNCF and Kubernetes Code of Conduct. With that, we only have one topic today in the agenda. Krishna Suri from IBM Research wants to present a CAP. You can take it away.
Sure. Yeah, thanks a lot. Please give me a minute before I share my screen. Okay. Sorry for the delay. I hope you are able to see my screen now.
Yes.
Okay, very good. Okay, so this is a presentation about our proposal on Peaks plugin. So this is a scheduler plugin, Peaks, and this is the same presentation that we have used during the KubeCon 2024 Europe a couple of months back in Paris. So I hope this is fine to use the same with very minor edits from that version. Okay, here we go. So the motivation for this Peaks plugin is the Kubernetes scheduler framework supports multiple plugins, enabling the scheduling of parts and nodes to optimize various objectives. However, within the ecosystem, there lacks a solution specifically designed to optimize power efficiency while simultaneously fulfilling other scheduling goals, which we see as an opportunity for the addition of Peaks. And Peaks addresses this gap by incorporating power efficiency as a scheduling criteria alongside other objectives such as optimizing resource allocation or adhering to specific topology requirements. So the goals of our proposal is provide a configurable scheduling plugin to minimize the aggregate power consumption of the cluster, implement this feature as a score plugin, and also avoid altering the behavior of default score plugin unless it is necessary, right? So with that, this is a quick overview of our solution that the power efficiency aware Kubernetes scheduler. The scheduler plugin aims to optimize the aggregate power consumption of the cluster during the scheduling process across all nodes of the cluster. It uses pre-trained machine learning models corresponding correlating node utilization with the power consumption for each node to predict the most suitable node for scheduling workloads. And these predictions are based on the resource needs of incoming workloads and based on the real-time utilization of the nodes within the cluster. So these are the two parameters based on which the assignment of a node for incoming pod is identified. Okay, so we will little bit dig deeper into what exactly this means, right? So when the process starts, we have to first create a power model for each cluster node. Okay, so assume that these are the cluster nodes, and we have to create a power model, and this is per scheduling cycle. This is the least the granularity level is per scheduling cycle. Of course, one can use the same power model across scheduling cycles as well, right? As long as there is no change in the characteristics, we can reuse the same power model which is used in the previous scheduling iteration as well in the current iteration too. But if you don't know, probably then you should start with first identifying the power model for each node. So the power model is actually identified using the node usage metrics as well as energy consumption metrics. So these are the two specific values that are used during the power model computation, right? So at the end of this phase, we get a power model for each of this node. And because these nodes may be heterogeneous or homogeneous, even though they are part of the same cluster, it is recommended that you compute this power model independently for each node. Okay. The next step is get the resource need for a part to be scheduled. So this is the incoming part, which is to be scheduled on this cluster. And this is a typical part specification, and it contains details about the resource requirements for that part. For example, how many CPU are required at the same time, like limits. If memory is also specified, sometimes it will be available in this section, right? So you can have access to the resource requirement for this part. And then you need to do some processing per node. The processing is as follows. Consider a cluster node and its power model, right? We have already computed the power model corresponding to the node that we are considering, and find the change in the utilization if the part is to be scheduled on this node. Assume that the incoming part is to be scheduled on this node, then the utilization of that node will increase, right? So compute how much is that jump in the utilization. Now, corresponding to that jump in the utilization of that node, find how much is the change in the instantaneous power consumption for that node. Okay, so how it can be computed, we will see in a while, but it uses what is the current utilization and how much would be the change in the utilization. So these values it will use, and once this is available from the plugin score. Okay, so the right side, the same thing is provided in pictorial format. We have the node and its corresponding power model. We have a part and its corresponding specification. Then we can compute first the change in the utilization, assuming this part is to be scheduled on this node, and correspondingly for this change in the utilization, how much is the change in the power consumption, right? You expected change in the power consumption, you compute that. So you need to repeat this for each node in the cluster, right? The expected change in the power consumption for each node, assuming this part is to run on that node. And once we have this information, so what we do for each node, we repeat this process, and there are more cluster nodes. Then we need to iterate this until all the cluster nodes, we try the same thing. And once all cluster nodes we iterate, then at the end, we normalize the plugin scores across all the nodes, right? And when we do the normalization, the philosophy is high score for a node with the less change in the power consumption. So whichever is the node with the expected power consumption value as less, so that is considered to be the more efficient node for the power part placement, and hence the normalization score is supposed to be higher for that particular node, right? So this is processing across nodes. After we compute this per node, we do it across nodes. And once we compute the normalized score, then we have to choose a suitable weight for peaks plugin in the Kubernetes kube scheduler configuration. As you know, the kube scheduler configuration can allow multiple plugins. We can have variable weightages for different plugins, right? So you can appropriately decide how much has to be the peaks plugin corresponding weightage in the kube scheduler configuration. And then with that, the scheduler prioritizes to choose a node with high normalized score during the pod placement, right? So accordingly, the scheduler will identify a particular node for the part. Assume that there is no other plugin that is in action, and only let's say Peaks plugin is there. Then the placement is purely based on the Peaks normalized score. On the other hand, if there are other plugins also, then accordingly, based on the assigned weightage, the part will be placed on a particular node. And if there are more parts to place in a given scheduling iteration, then we go back and repeat all these steps. If there are no more parts in this scheduling cycle, then this terminates this loop, right? So this is the bigger view of the overall workflow that is involved in peaks. Now, we will a little bit dig deeper into the power model training and inferencing aspects, right? So the power model training, for that, we can run some benchmark workloads and collect the metrics, namely, let's say CPU utilization and power consumption. We collect for each node after running some benchmark workload. Typically, this benchmark workload is representative workload of the real workload that is expected to run once the cluster is ready for executing workloads, right? So the next one is we train a ML based power model for each node using the metrics data. We have collected now the node utilization and power consumption information for each node, and now we can actually train a ML model using these metrics for each node independently. And inside the Peaks plugin, we import the power model parameters for each node. So please note the fact that the power model training is not part of the Peaks plugin. Peaks plugin only expects the parameters that represent the power model for each node. So we have to input the power model parameters for each node into the Peaks plugin. And if the power model is retrained at any point in time for any particular node or all the nodes subsequently, and if the model parameters change, then we need to update the Peaks plugin with the updated model parameters, right? And which can be achieved by via webhook and so on. Okay, so this is during dynamic during as the time progresses. If there are changes in the power model parameters, for example, a node is upgraded with more memory or more CPUs, then it is the time for updating the power model for that particular node. Or node is some CPUs are removed from that node. Maybe that is the again another triggering point for retraining the power model corresponding to for that node. Right, so these are some examples. So the power model training and inferencing. So this is the bigger picture that we have covered already. And the prerequisite modules for this are we need to collect the energy metrics, for which Kepler is one package, software package which can be used. And we need to collect the node utilization metrics, for which the node exporter can be used. Okay, and load watcher is another module. Probably I will call it as optional module, but the advantage with load watcher is that whatever is the node utilization metrics collected from node exporter, we can actually do some pre-processing and carry out some kind of caching, so that the retrieving the node utilization metrics is more efficient. So which is the objective of load watcher. So these are the prerequisite modules for this Peaks plugin to run. And what we support is we support the bring your own power model philosophy that best represents your node behavior, right? So as I already have called out, training the power model is outside the scope of Peaks, right? So one can actually train their own power models that best represents the clusters, the nodes of their clusters, and just input the configure the power model parameters inside Peaks plugin for each node. That is only the requirement. Peaks just inferences the power model, right? So that is the power model's scope within Peaks. Here are a couple of slides on the experimental evaluation of peaks. Peaks plugin is already implemented and available. I will show at the end of it where the code is currently available. And we considered actually 2 nodes in the cluster for the experimental evaluation. One node being a less energy efficient node, another one is more energy efficient node. This one, node 1, Tantwai 1 is more energy efficient node, and node 2, Tantwai 2 is less energy efficient node. And these graphs correspond to the utilization versus power consumption for each of these nodes. So if you see, the blue one corresponds to the node 1, which is a more energy efficient node. So if you can see at any point utilization, the energy consumption for node 2 is higher than the energy consumption for node 1, which means that node 2 is less energy efficient than node 1. That is because the configuration of node 2 is higher, right? For example, it has more memory, it has more CPU cores attached, and so on. And this is the sample power model, right? So here are few use cases that I would like to quickly take you through, which can actually help realize the advantage of peaks. So deployment of a pod via Kubernetes scheduler, scaling of a pod via horizontal pod autoscaler, similarly kubectl scale. Here with kubectl scale, we can have different types of API objects like deployment, replica set, replication controller, and stateful set. In all these, with all these API objects, it's possible to realize using peaks the suggested energy savings. And the migration of a pod, this is another very useful scenario. And shutting down of a cluster node, this is the 5th one. We will quickly take a look at it. The use case 1, deployment of a pod. So our cluster has 2 nodes, and we experimented using peaks as the default, using peaks as the scheduler plugin versus the default scheduler plugin. And the default scheduler plugin actually can place the incoming pod and any one of these nodes, right? So assume that the default plugin has placed the incoming pod on the energy inefficient node, okay? Because it can place on any of these nodes randomly. On the other hand, when the pod is run, when a pod is run on the 2 node cluster where peaks is the plugin which is configured, then peaks knows the energy efficiency of each of the nodes, and hence it chooses the most energy efficient node and places the pod on that. And at the end of running this pod for about 10 minutes, we see that there is a difference in the energy consumption across the cluster, across the both the nodes. And this is this difference in the energy consumption is increasing as the time progresses, right? So this we have plotted this for about 10 minutes. We ran the pod, and during that time, the utilization of the CPUs was around, node utilization was around 12%. So the point to note is here is that if the node utilization actually increases, and also we ran this experiment for more time, then we can see the energy savings, more amount of energy savings. Okay. So the second use case is scaling of a pod. So using horizontal pod autoscaler. So we demonstrate Peaks plugin where Peaks follows something called packing of pods on nodes, whereas the default plugin, it spreads the pods on nodes, right? So under these 2 scenarios, we will see what is the impact of using Peaks, right? So this is the default plugin scenario. In this case, initially we started with 1 pod, and we have configured the horizontal pod autoscaler such a way that the maximum number of pod instances can be 30. And as and when the CPU utilization goes beyond 50% across all the current number of pods, and as new workload coming in, the pods will be scaled up. So this is what this statement corresponds to, this command corresponds to. So hence, when we increase the workload, so what happened was that initially a pod was placed on one of these nodes, and as workload is increasing, it is the default plugin is following the spreading of parts on nodes, right? This is the strategy. So it alternatively started creating new parts across these two nodes, and hence we see at any point in time the utilization of these nodes is almost the same, and it keeps going that way. On the other hand, if you repeat the same experiment, that is, you start with the less load and keep increasing the load, and with peaks being the plugin, it starts actually placing the parts on the most energy efficient node until all the resources of that node exhaust, right? So this is the place where the utilization on the energy efficient node reaches 100%. Okay. Whereas here, we can see both the nodes are used for the deployment of parts, for running parts, and utilization here is reaching around 60% on both the nodes. Whereas here, for this node, which is most energy efficient, because Peaks plugin has placed most of the all the parts on that node, its utilization has reached 100%. Then you can see the utilization of the other node, which is energy inefficient, starts increasing. So the same thing, if you see over time, how much is the aggregate energy across the two nodes of this cluster. So you can see the orange line corresponds to the default plugin, and blue line corresponds to Peaks plugin. There is the gap. So this is the amount of saving at the end of uh, each of these time intervals. At the end of time 40 units for 40 time intervals, this is the amount of saving. At the end of 50, this is amount of saving. So as you run go towards the right, you see more energy saving, and here you can see the energy consumption using Peaks start increasing. That is because we are now starting we started using the energy inefficient now. Okay, so you can see there is a saving using Peaks with HPA. The third scenario is kubectl scale. So initially we have assumed that two parts, and both the parts are assumed that they are scheduled on the most energy efficient, that is node 1, Tantwai 1. Now assume that we have scaled up the parts from 2 to 5. So it's very simple to do that. Kubectl scale replicas 5. This is the desired number, and what is the deployment, we specify it. Then it will create the 3 more parts, right, to reach to the desired state of 5 parts. And the new parts are, in this case, using default scheduler are based on Tantwai 2, because it is following a node part spreading topology. It is placing these parts on Tantwai 2, which is energy inefficient. On the other hand, if you repeat the same experiment with the Peaks being the plugin, scheduler plugin, which is configured, then you can see the 3 new parts getting added to the node 1 only, which is, this is because this is the most energy efficient and there are enough resources to deploy this part, and hence Peaks plugin decides to use that node as the candidate node for the pod deployment. Okay. So the fourth use case, next use case is migration of a pod. In this case, assume that we started with there are this is the initial configuration, and there are 2 parts, one on each node. And when you delete one of these parts, then because we need to maintain 2 parts, right? So the delete the part, because we deleted one part, a new part is getting created on the Tantwai 2. So we deleted the part on Tantwai 2 because Tantwai 2, this is the node 2, is not energy efficient. So when we delete this part, the default scheduler plugin is creating a new part again on the same node. On the other hand, with Peaks as the scheduler plugin, if you delete this part, then we were deleting the part which is running on a energy inefficient node. Why we are deleting? Because there are resources on the energy efficient node. We wanted to actually utilize the resources of the energy efficient node, right? Until that gets exhausted, ideally we want to use energy efficient nodes resources. So that's the reason why we wanted to delete this, with the hope that now it will get migrated to the node one, and which actually happened with the Pix plugin. And this actually mimics pod auto migration. And why in the first place this pod was not configured on node 1 Tantavai 1? Because at the time of the deployment, maybe because there are other deployments that are using the resources of node 1, and hence there is no space for deploying both the parts corresponding to this PHP Apache deployment on Tantavai 1, right? Hence, one of the part was placed on the energy inefficient node. But after a while, the CPU stress test corresponding parts are completed, and hence resources are freed up, and we have now enough resources to migrate the part from energy inefficient node to energy efficient node. And that we are mimicking this auto migration using manual delete command. But actually our plan is that we can actually um, automate the same process using cron jobs and so on. And it is very easy actually to achieve the same thing. The fifth case is shutting down of a cluster node. This is the last scenario use case under which we can realize savings, energy savings using Peaks plugin, right? So we have seen in the previous use case migration of a pod from energy inefficient node to energy efficient node. So can you actually do the same thing?
One note here, we only have like 10 minutes left, so maybe this feels like the same use case as before, so maybe we can move into questions, or I guess my question for you first is, what are you looking for in this meeting?
Okay, so in this meeting, we are actually we wanted to first explain our proposal and want to see what is the next step in order to submit a CAP proposal. Can we go ahead and submit the CAP proposal? Given we have the implementation, everything ready, these are the repositories where the Peaks plugin implementation is available. Can we go ahead and submit it, or is there any prerequisite before we submit Peaks?
I suppose you're targeting the scheduler plugins repo. Is that correct?
Right.
Yeah, the requirements for that repo are not very exhaustive. Right now, I think the primary approver for that project is Wei, who unfortunately couldn't be here today, but I'm sure he can review offline and watch the recording if necessary. Basically, in addition to the design, we typically put a note on the production readiness status of this proposal. Maybe here, from what I can see, something like maybe like limitations you could highlight. I think I can see two limitations. One is that you have to do this for kind of like tailored for a specific cluster, right? Because you have to train for the specific machines you have. That's one. And two, I'm not sure how much this can be extended to cluster auto scaling, like scaling up. I suppose it doesn't really apply because if I understand correctly, you're targeting mostly on-premise clusters. So scaling up is, I guess you never scale. You might power down nodes, right? But you would never like add nodes infinitely or like you wouldn't put this in a cloud, I think, because you don't know what's the power output of the nodes you don't have yet.
Yeah,
Yeah.
so I agree. The prerequisite is that for any node that is to be added to a cluster, we need to have the power model specified so that it can be configured in Peaks plugin, right? Only then the plugin scores can be generated. So if I understand the query correctly, yes, the one of the limitation is you need to have a power model for each of the nodes. There can be alternatives assuming that you have homogeneous configurations of nodes, then you can actually have a library of parameters which specifies if this is the CPU model and these are the number of CPUs, this much is the memory associated with that node, and if this is the sample workload, then this could be the power model which one could use, right? It's not
Mhm.
necessary that you need to always fit that power model. You may start with the nearest power model, but for better accuracy, it is recommended that you need to bring the exact power model corresponding to that node. So, and in our opinion, what we see is that this is one-time thing, assuming cluster has static configuration, that is the number of nodes is probably not changing too dynamically, and the each node configuration is not changing too dynamically. You probably don't need to do it again and again. Only when there is a change in this any of these configurations, you are forced to redo the power model, and only for those nodes for which there is a change in the configuration. And the second one, the auto scaling, I'm not sure whether I have understood your query correctly, but one of the use cases here says that the Kubernetes plugin can actually work with auto scaling.
I
Which,
was referring to the cluster autoscaler. So adding nodes.
yeah, yeah, this is the cluster autoscaler, and here too, Peaks plugin is nothing but just another plugin, any Kubernetes plugin, and um, the same operational um, uh, rules and constraints and limitations apply for Peaks plugin also. I don't see in particular any reason why uh, it cannot work with the cluster autoscaler. For example, in this use case, what we have demonstrated is we have a two-node cluster, and we have migrated all the parts from the
My
energy and
my point here is that, well, you have to know which nodes you're gonna get and have the model for those.
of course. Yeah,
If that's satisfied, then you're fine. If you don't have a new model, then the plugin, like if you scale up to a completely new node
yeah, yeah,
that has a completely different architecture, whatever else,
sure.
um, so that would be kind of like the limitation.
Yeah.
I think it's minimal in the sense that probably most clusters, most setups will have a common set of nodes. So yeah, that in that case is probably not a big
Yeah,
limitation. But yeah, in any
I
case,
completely agree. I
it
completely agree.
mhm. It sounds like yeah, this is kind of like a good fit for the scheduler plugins repo. Um, Something I would always ask is whether there's a repeated plugin that kind of does the same. Um, there is in the scheduler plugins repo, there is the trimaran plugins, which are not directly focusing on power consumption, but they are focusing on live usage.
Right.
which can be related. Although this model is a bit more static, which in a way might make it a bit more reliable, or more predictable at the very least. But yeah, I think there is no direct replacement, or yeah, you're not reinventing something that is already there. So I don't see any major problems to
Sure.
getting this merge.
Yep.
But again, the owner of that repo is Huang Wei. So whenever he is available, he can or you can double check with him
Oh,
if he has any other any other concerns.
okay.
Just to add a comment, if you don't mind, the reference to Trimaran, I think, is a very good one. That's the most relevant. And as you said, Trimaran is concerned about utilization and not power, whereas Peaks combine both utilization and power. I presume that Peaks is going to use I mean, at least it's using the load watcher, which is a component that Trimaran is using to get the utilization. So that's the commonality between Peaks and the Trimaran plugins. If
Oh,
I may
okay.
ask a question, Krishna, thanks for the presentation. You mentioned that you have this independent of the plugin, some component that is somehow either learning or creating the power model. And my two questions are, how are these parameters of the model passed to the plugin? Are they going to be like, you envision that to be labels on the nodes, a custom resource, something like that? And secondly, this other, the independent component, do you envision that as some kind of an operator running in the cluster, that its all sole objective or function is to go around and look at all the nodes in the cluster, and based on the data that it has seen from load watcher, it will create that power model and put the parameters in whatever means it is.
Yeah, sir. Thanks a lot for the questions. If I understand correctly, uh, uh, the first question, right? How the changed parameters, power model parameters can be passed to the Pix plugin. So for that, currently what we envisage is a webhook model. We can have, for example, a webhook, but there are other things like um, uh, configuration settings, right? It can be a configuration parameter, and we can dynamically change the configuration value, which can be read from inside the plugin, Peaks plugin.
Okay, thank you.
Yeah, I guess in that topic, it might be worth exploring a few options on how the model can be passed, maybe so that it can be updated
Yeah,
without having to restart the scheduler or things like that.
yeah, we don't see any reason to restart the scheduler. It can be a configuration parameter which can be set dynamically, and whichever is the in a current scheduler scheduling cycle, the value it can be directly referred from the environment variable and used actually.
Okay. Well, yeah, all those details have to be in the design proposal in the CAP. But yeah, other than that, we'll just see from the CAP.
Sure. Yep. Thank you. And there is, in fact, just to add, there is a PR um, to address the same thing. There is an issue that is already open to address this, updating the model parameters into peaks plugin dynamically.
I see. Okay. All right. Yeah, I guess please open an issue in the schedulers plugins repo and just submit the PR, and Wei will take it from there.
Thank you.
All right. Thank
Thanks,
you, everybody. That's
Thanks.
time for our meeting. See you next
Bye.
time.
Bye-bye.